And now moving on to the next presentation, Andre Lopes, Head of Product Engineering at 3S Solar Plus, is going to talk about high energy density hybrid PV modules for space constrained areas. And Andre contribution is part of a Hiperion project. Andre, the floor is yours.
Good morning, everyone. Thank you, Mr. Chairman. I will quickly share my screen. Can you see my screen?
Not yet. Yes. Now we can see your screen.
Okay, so today we'll be talking about high energy density PV modules for space constrained areas. My name is Andre Lopes. I'm head of product engineering at 3S Solar Plus and part of the consortium of the Iperian, which is funded by the European Union. Before I start, I just want to thank to all the partners that provided some of the data and information that I will be sharing today. So the presentation today will start by presenting with 3S Solar Plus, why we are interested in this technology of Iperian, explain a little bit about energy density concept from the Iperian model perspective, then go a little bit into the first results from the LCOE calculations and comparison with our technologies, then going into the life cycle assessment preliminary calculations as well, and then draft some conclusions. So 3S is a company which is an old new company. We were actually funded in the year 2000s, focusing on BIPV. 2010, we were acquired by Meyer Burger. Actually, we were fused with Meyer Burger. And by then we had 3S Module Tech and 3S Photovoltaic. So our DNA is actually expertise in machine building to produce modules and PV module manufacturing. And in 2018, we were acquired back by the original founder. And since then, our strategy has been to focus on BIPV. And our goal is to repurpose building surfaces. We focus on producing building material that can be applied on roofs, facades, balconies. And this building material is, it is to protect the building, it's to comply with the standards and regulations from a building industry. Also has to provide energy, so it needs to comply with all the energy standards and regulations. And it needs to be aesthetically interesting. So architects and final customers acquired the PV modules. And to do that, we do a lot of innovations in our modules. We add color. So what we do is to add ceramic enamel to the glass, or we also do pigmentation of foils and we add it to the glass, or we add glass structures to decrease the anti-glare of the PV modules, like in the picture on the right. Or we have to comply with roofs with extremely complex roof features and with a lot of shading, and obviously the forms, shapes, and space constraints that objects have by themselves. So all of these topics tend to always reduce the module performance. So that's why we were since the beginning very interested in the concept of energy density that is introduced by the Iperian module. So this Iperian module, it's actually combining 3 technologies in one module. So we have the micro concentrator PV and then the micro tracking, which is integrated into the module. And we then add on the back a set of secondary cells that try to capture the diffuse light. With this stack of technologies, what is achieved is actually 160 watt of nominal power. And these, we're talking about a module which has 0.6 square meters approximately area, and adds on top of that a diffuse capturing light of up to 40%. And this is resulting in about 30% efficiency and up to 60% more energy per area than the conventional crystalline silicon modules. So, and before I proceed, this is the setup. So we had a problem. There is Iperian module, which is a very interesting technology. We are participating in the Iperian project to answer three important questions, 3S and the group of partners, which is, would 3S be interested in producing these modules in the future? So from a manufacturing perspective, is it interesting? Second question is from an end customer perspective, utility scale installers, commercial, rooftop for self-consumption, or BIPV installers. Is this module interesting? And if so, which area would be the most interesting for the use case of this module? So this is one of the questions we try to answer by the end of the project. And obviously, nowadays it's more and more important is to look at the environmental profile of this module, because if you're talking about energy density, what is this resulting in terms of the environmental profile? So going to the next slide, I would like to show what does energy density means in the context of the Iperian module. So like I said, we have a different stack of technologies on top of each other, and these result in a compound addition of energy. So we can see in the graph on the left that we have the crystalline silicon cells and the concentrated PV working together at different times of the day and with different contributions. And I'm not sure if all the attendees of the conference were present in the last days, but to quickly show how the module works. So maybe the lenses on top of the module concentrate some of the light into the multi-junction cells, high efficiency cells, and the secondary cells, which are represented here in violet, they absorb both direct and diffuse light. So we have these two sets of cells that work together to produce energy, and that's why we have a compounding use case of production of energy for these modules. And this makes it very interesting. So with these preliminary data, and we will be in our work package with all the partners, be checking real pilot installations, but we are still too early in the project. So we are relying on data provided by the research institutes in Madrid and Fraunhofer. So with the data they provided, and we built the LCOE model to try to understand where these modules are standing facing the competition. So we actually had several different cities, but I'm just using here, for example, Lyon in France to understand where the preliminary results of LCOE are putting the Iperian module, which is presented here with black plane. So CPV, it's if we only consider the concentrated PV, with backplane with secondary cells, and we can add bifacial and axis, but we are actually focusing on the Iperian only on the secondary cells added to the CPV part, and preliminary results show that we are above, a little bit above the competition, 2 to 3 cents per kilowatt hour. And this is actually expected since the beginning. And I'm going a little bit deeper into these results. But before that, I just want to show that on the left, we have a map that represents that LCOE is dependent, obviously, not only on radiance, but financial incentives, retail price of energy. And this is going to be important to understand what could be interesting use case for Iperian module. But I just want to make a caveat. We are at the moment at about halfway of the Iperian project. So a lot of information related with the BOM cost, energy production, lifetime data, they're preliminary. So they would be updated as the project carries on. We already know with the preliminary data that it will be hardly competitive with standard modules under normal conditions. And adding on top of that, and as we have been watching in this virtual conference, there is a race from all cell technologies for increase the efficiency. So standard modules under normal conditions is not the objective of competing at the moment as we see it for the Iperian modules, but we see an extremely interesting solution when restrictions exist. And what I mean by restrictions, I mean space constraints or production objectives. So for example, if you see this graph or this map on the left, where we see where PV would be most economically interesting. If you look at Europe, we can see that obviously South countries because of the solar potential, but we also see that countries, for example, that are border, Greece and Bulgaria, they have the same irradiation, and in Bulgaria, for example, it's not competitive to install rooftop PV, but in Greece it is. This means that different countries have different incentives to install PV. So from a Iperian model perspective, if you are looking into a good solar potential, if the country has favorable finance and rather high retail prices, it becomes interesting for the rooftop installation of generally PV. But if you add on top of that space restrictions, so let's look at a city where we have a space restriction, we have high-rise buildings with a very little available real estate on the top. If you add on top of that electromobility, which is going to be a trend in the next year, so the consumption from these centers will increase, and these will likely increase the grid congestion and the dispatch costs. So we see the perfect recipe that will make energy dense modules relevant in the future. So this is from an economical point of view, and we know that nowadays, if you don't talk about the costs on the environment, it's incomplete explanation. And it's part of this project also to look at the life cycle of this module from an environmental perspective. So this module is quite interesting. We have a different stack of technologies. We have a different layup, and we were very, very interesting since the beginning to see what would be the contribution of this added. For example, we have lenses on top of the module made of PMMA. We have a backplane, which is a monolithic backplane with primary and secondary cells. We have micro actuators inside the module, increased frame, and will be very interesting to understand what is the contribution of all these from an environmental perspective. And as generally is the case in the PV industry, PV cells do tend, and this is for generation 2, the latest generation, do tend to be the biggest contributor of greenhouse gas emissions. And then we have the lenses on the top, PMMA 20%, and obviously then the aluminum frames. What I think is interesting and what I want to share in terms of this graph is the secondary cells, which produce the least amount of energy, are actually producing most of the environmental contribution. So this means also that the cells that produce the most of energy have very little or almost negligible environmental contribution. So it's an interesting concept. So using these preliminary results we had, and in order to compare it with different technologies, so the metric which is normally used is the CO2 kilograms or grams equivalent per kilowatt hour produced. So we assume the lifespan of 25 years for these calculations. And 2 locations, just to give an example. And for example, we have Madrid, and we are about 17 grams of CO2 equivalent emitted per kilowatt hour, and Lyon with about 23 grams. How do these compare with standard energy mix or photovoltaic technologies? So here we have a graph, and this is from the European Energy Agency. At the moment, the European energy mix is about 255 grams of CO2 equivalent per kilowatt hour. So Iperian modules are delivering about 10 to 15 times less impact on the environment. And since we also have data from our own modules, 3S modules, we know that our modules are about 30 to 35 grams of CO2 equivalent per kilowatt hour. So this also means that we're talking about almost half of the environmental impact when we compare Iperian modules to our standard 3S solution. So I think this is an interesting finding because energy density is not only on the LCOE level, maybe having good results, but also on environmental impact. So as a conclusion, we understand that BIPV tend to reduce the model performance. This is a given, and it will be interesting case for Iperian modules if given that they increase energy density. LCOE shows promising application potential if space constraints and production objectives exist. And LCOE results, LCA results show a clearly low grams per CO2 equivalent per kilowatt hour produced when compared with other energy sources and photovoltaic elements. So that's all. Thank you, everyone. Hope it was clear, and any questions, please don't hesitate to ask. So I give you back the presentation, Mr. Chairman. Yeah.
Thank you, Andre. I think there are also questions in the chat window. I already see one question. It would be great you can answer in the chat function so that we can move ahead with the panel discussion.
Great.